Okay, so welcome everyone to the next Arc Science seminar. We are very glad to have Nicolas Libedinsky from Chile, and he will be telling us about an introductory survey or intro survey of representation theory. Over to you.
Thank you, Apurva. Well, first of all, I would like to thank Apurva, as I do in the paper, because this paper and this talk are essentially due to him. I was, I had just had a baby. He was Gael, 1 month when I started writing this, and it was like really probably something I would have never done for myself, but now I'm really happy that I did it, because it's like fun to read and it was fun to write, and Apurva helped me a lot. So, well, let's start with the talk. Maybe I put here the title a little bit big of your seminar, and so, but my name is here. If you see, this is me. That's my name.
Very nice. Yes.
Okay. Yeah. So I will give a very something like, usually representation theory is justified, or mathematics in general is justified by its applications to other stuff. I will try to not do that and to explain why I think it's important in its inherent beauty and in its inherent coherence. And then I will jump 100 years and speak about the last things very quickly, but trying to give some kind of overview. So this is a citation by Grothendieck that I love because it's very powerful defense of group theory. So it says that the introduction of the cipher 0 or the group concept was general nonsense too, and mathematics was more or less stagnating for thousands of years because nobody was around to take such childish steps. So groups are extremely basic and fundamental in a way that mathematics was stagnating before it was introduced by Grothendieck, that it's not like a particularly stupid person. So when you get to, that was my introduction to groups. I like to say that groups are important, but when you encounter a group, you can ask two basic questions as when you encounter anything. Essentially, how are you inside and how are you outside? So what are you made of is the question A, and question B is how are you perceived by others? How do you relate with others? And that is essentially representation theory. But let us start with point A. It's what are you made of? Because this is something probably some of you know. This was when they tried to understand this for finite groups. The question was, they had a program. So the question was, find first all, sorry, 1 second. All finite simple groups that they thought as the building block. We think about them as the building blocks that form every finite group. And part 2 is to understand how they glue together, how they, if you have all the simples in the finite groups, how do you glue them together to form another group? So all the possible gluings. And for question A, 1, this is probably the biggest collaborative effort in the history of mathematics. Maybe I'm wrong. If I'm wrong, I would like someone to tell me, but it's amazing, like the number of mathematicians that were involved and the time elapsed. So from 1832 to 2004. And finally, they got to produce a list of all the finite simple groups in 2004, and they are the very, very easy Z over PZ, the alternating groups AN with N bigger or equal than 5, and we know that these are groups that are important for also for in Galois theory and stuff like that, for constructible for all problems. The others are group of Lie types, like the projective special linear groups, the projective symplectic groups, and others. And then there are 26 sporadic groups that they have all very interesting names. And it's kind of a crazy list, like not at all what you would hope in principle. I mean, like the concept of being simple finite group, it's kind of a very like basic concept, and you would hope for a kind of basic unified solution, something like, I don't know, like some blah, not like blah, 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 blah. And most of all, this is like the part that I feel that it's unsatisfactory. Like you would like to understand these sporadic groups in other terms to understand. But anyways, this is like this is the solution. We know now the solution. And in my intro survey, this is probably the most important part of the intro survey, where I explain the difference between what you think about part 2 of the problem. So part 2, I remember, is this, understand how they glue together. You imagine them as bricks, the simple, finite simple groups. And this is, you imagine how they glue together. And this is in reality, how they glue together. So I will close up. This is the monster group. Okay, so now we go to part B. It's how do you behave? So first of all, we have to decide what groups shall we study. And there are 2 favorite groups for me, but in the intro survey, I didn't explain why they are my favorite groups, and I want to explain why. If I ask you, what are the things in mathematics that you like, that you feel the most comfortable with, probably many people will say a set or a vector space. This is like the, yes, exactly. In the chat, we have the solution. So if you start with these extremely basic objects in mathematics, and you look at their symmetries, their symmetry groups, you obtain the symmetric. If this set has cardinality n, the symmetries is Sn, the symmetric group in n elements. It's isomorphic to that. And if you take the symmetries here, you obtain GLV. Yeah, the linear functions that are invertible. And here, these are the functions that are invertible. There's no linearity. Here you want to respect the linearity because you are in a vector space. And so I make a little joke in the intro survey that these groups are so important that even every subgroup of them has a special name. So the subgroups of GLV, they are called linear groups, and the subgroups, and here is the punchline, the subgroups of Sn are called finite groups. Okay. So now we have our groups. We have our groups that we want to study. And I want to say that I found this quote by Andre Weil, that it's allegedly clearly the most genius person in the 40s and maybe 30s. He was like an absolute genius, and he says something beautiful that I will read. Nothing is more fruitful. All mathematicians know it. I think he exaggerates. He's exaggerating that all mathematicians know it, but that's what he believes. Nothing is more fruitful, all mathematicians know it, than those obscure analogies, those disturbing reflections of one theory in another, those furtive caresses, those inexplicable discords. Nothing also gives more pleasure to the researcher. The day comes when the illusion dissolves. The yoked theories reveal their common source before disappearing. As the Gita teaches, one achieves knowledge and indifference at the same time. So beautiful. And I will show you a little bit of this, exactly these obscure analogies, disturbing reflections of one theory in another, furtive caresses, and the inexplicable discords that make me very uncomfortable about what I will explain now. So let's go to 1951. Steinberg realized that sorry, this is the rest of COVID. So he remarked that the symmetric group and GLM over FQ, where FQ is the unique field with Q elements, with Q a power of a prime number. So it's a finite field. Sn and FQ have remarkable similarities, he realized. He even used this analogy along with the representation theory of the symmetric group to understand an important part of the representation theory of this group. So it was like important for his work. But then Tits came in 1957 and he said something mind-blowing. He said, the symmetric group is GLM over the inexistent field of one element. And this is like crazy, absolutely crazy, because the field with one element does not exist. Like, and what you would say, like, okay, like imagine that you define in F1, you just define that you know a field has a 1 and a 0, so at least it has two elements. But you can be naive and say, well, let's say that 0 is equal to 1, and let's see what happens. But then a vector space over F1 would be 0. Because every V would be 1 times B, that would be 0 times V, that it would be 0. So that's not really what we want. I will explain in what sense he was saying this. And also I will explain the inexplicable discords. But this is like very serious thing. Like it was not really taken seriously for a long time, this observation by Tits. But some 35 years later, many people started to work about this, like Kapranov and Smirnov, and then Manning proposed that the Riemann hypothesis might be solved if one fully understands the geometry over F1. So people like Soule, Cons, and Consani have worked over trying to understand the geometry over F1, and the main motivation is to prove the Riemann hypothesis. This is an approach. So I will explain. So F1, just to be clear, this does not exist at this point. But I want to stress that the cipher 0 did not exist at some point, or the imaginary number I. They were inexistent creatures for a while, but people kind of knew that they had some sort of existence until someone really put them in the right place, and now we think, okay, 0 and I, they exist. I think this will happen with F1. And so let me explain to you more or less what he meant. So let us define the Q integer nq just as this polynomial over that has integer coefficients over q. 1 plus q squared plus q to the power of n minus 1. Of course, when you decide that q is equal to 1, this is 1 plus 1 plus 1 plus 1, it's n. And so I will call this set 1, 2, 3, 4 until n by this letter, bold n. And I will say that a Q deformation or a quantum deformation, it will be, sorry, I have to cough a little bit. Okay, so this is a vector space, the n-dimensional vector space over fq to the power of n. But I will not take exactly that, but the projective lines, the projective space. So it's the set of lines inside this. And I will call this bold n q. And I will say that it's a Q deformation. And you will say, like, why? That makes no sense. And like a very little comment about why this, like, there are many relations with quantum mechanics, and that's why usually you speak Q deformations and quantum deformations. But one beautiful that I found here that you can see here is that in classical mechanics there is a set describing the states of a system. So it's a set. And in quantum mechanics or in quantum physics, the states are vector lines in a Hilbert space. So you have it are elements in some projective space, in the projective Hilbert space. So, well, that's a comment. But so why would you consider that this is a Q deformation? The reason is just counting. So the number of the cardinality of this set is, of course, n, and the cardinality of this set is nq, is the Q deformed, the Q integer n. Why? Because in total, here you have q to the power of n minus 1 elements different from 0, but every element appears, every line contains q minus 1 elements. So you divide, and this is exactly this. So that's a very simple reason why this is true. But this is, like, clearly not convincing enough. So, but I think that this will be convincing enough. So now that this set has the Q deformed cardinality of this set, it's okay. But now consider the natural subsets of this. So let's call nk the subsets of n that have cardinality k. And in the vector space analog, you consider nq, bold nq, k as the subspaces of nq that have dimension k. And what is amazing is that the cardinality of this set, nk, of course, is the combinatorial number, n factorial over n minus k factorial times k factorial. And if you calculate this, you will obtain the same with the q integer. nq factorial, of course, nq factorial is 1q times 2q times 3q. So that's, I didn't define it, but it's the obvious definition. And so maybe now we are more convinced that this is effectively like a Q deformation of this. And so, what is the symmetric group? The symmetric group is a set of all functions from n to n bold n, so 1 to n, 1 to n, sending sets with k elements to sets with k elements. Of course, that's the definition. That's a rephrasing of being bijective. And so the Q deformation of this should be the functions, the linear functions from NQ to NQ, sending the k-dimensional vectors, the k-dimensional vector spaces to themselves. In fact, it's unnecessary to say linear. If you say this, they are linear. And this is exactly the deformation of this, of course, but this is the definition of PGLN FQ. And this P, maybe it's not so relevant. I said that GLN FQ, I said that SN is GLN F1. Maybe I'm saying adding a P, but let's not enter in that. Just let me tell you something nice about this, is that the determinant here, the determinant function is positive if a basis of your vector space is sent to another basis with the same orientation, as you know. And this is exactly the determinant, so goes here to the sine function. The sine function that sends Sn to plus 1 minus 1. And okay, you would say, okay, like the sine function is the determinant is the Q deformation of the determinant. Sorry. The determinant is the Q deformation of the sine function. But what it's very striking is that if you see the kernel here, the kernel of the determinant, this is P SLN FQ. And the kernel of the sine is the alternating group. And why is this striking? Because they are both simple, except for very small n and q. AN is simple from n bigger than 5 side, and this is also simple most of the times. And this I found remarkable, really interesting about this analogy. So there is another analogy between, so I now explained how Sn is like GLN F1, more or less. There is another beautiful way in which they relate, that it's that Sn you can see as a subgroup of GLN FQ or GLN in general. So essentially you take the identity matrix, and you permute. For example, here I am sending 1 to 2, 2 to 3, and 3 to 1, and I permute here so I send this to this, 1 to 2, 2 to 3, and 3 to 1. And so I call this W dot. And if B is the upper triangular matrices, here I'm in S3 or in GL3. If B is the upper triangular matrices, then you have the Brouwer decomposition that you can write this essentially as a union, as a disjoint union of double classes with W in Sn. This is an absolutely beautiful and deep relationship between GLN and Sn. And the third one, it's called Schur-Weil duality. That it's kind of key for the development of modern representation theory. Brouwer decomposition too, but this is like very fundamental in relating. This is a duality. So now you are not seeing Sn, GLN as a deformation of Sn. You are not seeing Sn inside GLN, like constructing GLN, but you are seeing them as in equal footing. They are like kind of the same in some sense. So maybe I have to, I will go fast here, but essentially you have V, the complex numbers power n, so an n-dimensional vector space. So you have an action of GLV in, I will call V tensor n, this V tensor V tensor V tensor V n times. So you just act, G acting in a tensor product is G acting on each part. You have the symmetric group also acts here by permuting the variables. It permutes the V1, V2 and stuff. And so when you have an action of GLV in V tensor n, this is another way of writing this is a map from GLV to the endomorphisms of V tensor n. And this gives you a map. I will go fast here because I don't want to enter in these like details, but this gives you a map from the group algebra of GLV to this, that is highly non-injective. And I will do an abuse of notation, and I will call the image of this map, I will continue to call it CGLV. That's just for the formula to be beautiful. So Schur-Weyl duality says that the endomorphisms of these that are stabilized by the group algebra of the symmetric group, it's isomorphic to the group algebra of GLV. And the endomorphisms of V tensor n that are stabilized by the group algebra of GLV, it's exactly the group algebra of Sn. So you go from CSN to from Sn to GLV, and you go from GLV to Sn, doing the same process. And this is I want to show you the why I'm saying that this is like key in the development of afterwards, because following this duality, all the good stuff appear, or many of the most of the good stuff. No, not most, but like a lot of the good stuff. No, not a lot, like a little bit. No, not a little. Oh. So I slightly change here. It works also with SLV. So you have SLV, the special linear group, and the symmetric group, and you have this duality written as I wrote it here. So you have this double centralizer thing that you go from one to the other and from the other to one. Ah, sorry, I forgot one thing. So may I go back, because I forgot to say something about those inexplicable discords. What is the discord here? Why this is not so nicely this thing, the Q deformation of this is because when Q goes to 1, the cardinality of this does not go to the cardinality of this, but almost. There is like a Q minus 1 power n that appears. And this is like very annoying for me. And there are many ways to try to solve it. I try to write some in the Introsurvey, but it's like, it means that it's not exactly the thing that we need. That is the inexplicable discord that I wanted to say. So let's come back to our picture. So there is a quantum version of this. So the SLV, you will have the quantum groups. This was like a fundamental thing in representation theory when quantum groups appeared. They were like a revolution. And they essentially, there are several ways of looking at quantum groups, but they are, as I'm writing it here, it's a quantum deformation of the universal enveloping algebra of SLN, of the Lie algebra SLN. And here you have the Hecke algebra that was discovered in 1964. In the Introsurvey, I explained the story of how these things were discovered. And you have another this is called the quantum Schur-Weyl duality, and you again have that the end of BQ tensor, and that it's stabilized by this is this, and vice versa, and it's super beautiful. And I think that's enough for us to agree that these are the correct quantum versions of these things, or Q deformations. The fact that this thing, it's so incredibly beautiful, appears exactly here in the same level. And how do you go from here to here? Well, essentially, you just go Q equal 1. If Q equal 1, the Hegel algebra that I have not yet introduced and that I will not introduce, but it's a very Q deformation of the group algebra of the symmetric group. So like the symmetric group, you cannot deform like that. You cannot deform the group, but you can deform the group algebra. This is like a method of deforming, like when you cannot find a deformation, you you consider a structure that is equivalent. So the group algebra in representation theory terms is equivalent to the symmetric group. So you can study representation theory from the group algebra or from the group, and it will be equivalent. And here also the representation theory of the group SLV, the Lie group, say, or the algebraic group, and of the Lie algebra SLV, or of the SLN, or of the enveloping algebra of SLN, this is all essentially equivalent. So that's why here you deform the group, the enveloping algebra, the U of SLN. And major things were when you go to the higher level. So the highest level, it's kind of like the new thing, say, not so new, 1990 and 2008, but let's say the new thing. And here you have Sorgel bimodules. Here you have something strange, that it's a category, that it's kind of like, so this is a categorification of these things. And this is the Tukats-Moody algebra. And this is how do you go from here to here? There is you use the Grothendieck group. And if you don't know what the Grothendieck group is, don't worry. I will explain more precisely soon what this means, what this really means to categorify something. Of course, there's no definition really, but I will try to give the intuitive definition. Because this K0, it may not say anything to you. So after half of the talk, my conclusion is that GLV and SN are similar beasts. That was my conclusion. And now let's go to the question of how do they relate? And I find this funny, like, what are the group homomorphisms? It would be awesome to erase all of this. I will erase it so that you cannot see it. What are the group homomorphisms from GLM to the symmetric group? Are there a lot? And the answer is not a lot. There is only one. The answer is the trivial morphism. It's the only one. Why? Because phi of G is phi of G, so to the 1 over n, the n factorial root of G to the power of n factorial. So here I'm using a theorem that essentially every element here, you can find a root, some other matrix that it's invertible, that to the power of n factorial is your G. And that's like not hard to prove, but not super easy either, so I don't prove it here. So you have that it's some matrix to the power of n factorial, but Sm has n factorial elements. So here you can take the n factorial out, and this implies that it's the identity. So that it's as simple as that. There's only one map group homomorphism. So this is a bad question. This is not the question that you want. A question that has a trivial answer is not the question that you want, or not the question that I want. Maybe you want. Some people prefer questions with trivial answers. Cheers for them. Let us see another bad question, but with opposite reasons. What are the group homomorphisms from GLMC to GLMC? So let us be a little bit more humble and ask for m equal 1 and n equal 1. So the GL1C, the invertible maps from C to C, are essentially C cross, so C without the zero. It's isomorphic to that. Yeah, maps from C to C, they depend only on a non-zero complex number. So you want maps from C cross to C cross, and then we will be even more humble because this is already too crazy. We will ask only those that are the restriction from a field automorphism from C to C. So if you have a field automorphism that it's matched, there are not so many field automorphisms from C to C. When you take out the zero, it will give you a group homomorphism from C without the zero to C without zero. But already these are uncountable, and their construction requires the axiom of choice. Already this extremely little part of the problem. So that's why I'm saying that it's a bad question again, because it's like absolutely crazy. Like imagine how many are of these and how to construct them. We would love to say like they are parameterized by something that we know. If not, it's like a wild thing, no?
So here, of course, if they're measurable, then the problem is that they're not measurable, right? These field automorphisms. Otherwise, you have functional equations of Banach and Sierpinski. I think this is some analysis thing.
I don't know if they're. I don't know.
I think if they're measurable, there are fewer, but if they aren't, then anyway. Sorry, go ahead. Sure.
I don't know.
These are too many. That's sure. Yeah. Okay.
Yeah. Yeah, and extremely hard to construct. And so it like we have seen GL to SN, GL to GL. Well, I didn't consider SN to SN, but we can consider SN to GL. And this is a great question. This is a great question, and this is the original question of representation theory, to take your group and see how you see it as linear maps. And so there, I will not give an answer of this. I will just give the approach that I give in the Introsurvey, because I feel that always this thing is explained it's very complicated. So I want to give some insight about like what are these irreducible spect modules. So essentially you have that these maps are representations, and representations of the symmetric group of finite groups are divided are direct sums of irreducible representations. So the quest here is to understand irreducible representations. But for example, what happens when you have S3? S3 can act, well, it's acting on 1, 2, 3, no? But of course, I draw it as a triangle, but it not only acts on the vertices, but it, for example, also acts in the set of edges. If I take an edge and I permute 1 with 3, this edge will take it to this edge. So it acts in the set of edges, and it also acts in the set of faces, that there is only one, but and something that is key here is that when you are acting on a set, you are acting immediately in C of X. So it's the linear combinations of this. So for example, if I'm acting in the set of vertices, I will be acting also in the linear space that has where I put, for example, lambda, mu, and nu. These are real numbers associated to each vertex. So this is a three-dimensional vector space. And when I permute the vertices, I send this gives me a linear map from the C3 to C3. So that's what I'm saying here, that when you are acting in subset, you act immediately in the set of complex functions on this set. And so I will say, as I want to be very fast, I don't mention this in the intro survey. I try to avoid it, but in order to be very fast now, let's say that I have something like this. This is called a Young tableau. So it's something that it's essentially growing. So I have 1 here, 2, 2, 3. It's growing or non-decreasing in the number in here. So to this, I associate, I look in the bottom and I have 1. And so I decide to put 1 dot. Here I have 3. In the second stage, I have 3. So I decide I will put a dot inside a 3 phase. Here I have 5. And so I will have a dot inside a 3 phase, inside a 5 phase. And then I add the last 3, so I should have like the whole thing that I don't draw. So this will be my set. This is what I will call flag variety of lambda. The set of all 1 vertex inside of 3 vertices, inside of 5 vertices, inside of 8 vertices. And of course, you have an action of the symmetric group here. So for example, here I'm writing the action that sends 1 to 2, 2 to 3, 3 to 4, 8 to 1. And so when I send 8 to 1, I will have this vertex here. And it's like a rotation of all the thing. And so this flag is sent to this flag. And so I consider the symmetric group acting on the complex. So now to every flag, I give a number, a complex number. This is what I'm saying here. So it's the space where to each flag, I give a complex number. And so I have a lot of flags. And so it's a complex space of a vector space of complex dimension, the number of flags of lambda. And I can reflect this and I obtain the transpose of this diagram. And the key thing is that if you write this as a direct sum of irreducible representations of the symmetric group, here I added the sign. I will explain now what is the sign, but if you intersect it with this with lambda prime, here is lambda prime, with the sign. So here, if you act by the sign, you have mu to the associated to this flag, and then you do this, you will have mu times the sign of this. So you will have plus or minus mu every time. This is like another action of the symmetric group here. And I call this action, maybe sign should be out, sign here. Yeah, because it's not the flag. Sorry. It's not the flag with the sign, it's the C with the sign. And so the point is that it's these things are like the irreducibles are complicated to understand, but if you see it like this, you see that essentially in this space and in the dual space there with the sign convention, there is only one irreducible representation that appears in both. And so how do you collect this one? Well, given some theorems of representation theory, there will be essentially only one map from here to here, one map that respects the symmetric group action, only one. And the image of this map is the spec module, and it's the irreducible. And so that's what I wanted to say about this part of the problem. So, so what I'm saying is that the symmetric group, this question is a beautiful question. It has a beautiful answer, parameterized by beautiful things. and it's extremely important for many things. Of course, you could ask the question, what happens when you are not considering complex representations of the symmetric group? And this would be FP instead of C. And that's another world, but we will get there. So now I am going to do, I have 14 minutes, so I will do the fast forward 100 years, and I will do a summary of the work of my colleagues. And so I will explain only the things that I need to explain. So if you want more details, go to the paper, Introsurvey. So you have the complex, the group algebra of the symmetric group. You could deform it, and you have the Hecke algebra of the symmetric group. So this might sound complicated, but it's not complicated at all. This is a very concrete algebra that you can play with and calculate everything. And it has a basis. It's defined with a basis called the standard basis. You can prove that there is another basis. So for X in the symmetric group, there is some person that is called Bx, that some people call it the canonical basis or the Kashtan-Lustig basis of HSN, that it's a basis in this sense, that the Hecke algebra can be written as a direct sum. So the Bx is a basis of the Hecke algebra as a ZV minus 1 module. And the Bx are complicated to calculate in general in terms of the Hy, of the standard basis. That's like a very interesting and fun problem, and in some special cases give you all kind of this gives like extremely important information in representation theories. I think that maybe Apurva can correct me, but maybe I'm exaggerating, but there might be more than 1,000 results about saying like what representation theory, some representation theory numbers are in terms of these Kashtan-Lustig polynomials. There are these polynomials related to the Kashtan-Lustig basis. This is like ubiquitous in representation theory. Well, that's all that.
I had one question. I had one quick question though. So you said that, yeah, the Bx are hard to calculate in terms of the Hy in the Hecke algebra.
Yes.
Very naive question then somebody could ask is what happens if, you know, so when you set Q or V to be 1, then H of Sn becomes the group algebra of the symmetric group.
Yes.
So under that transfer, so the Hy's translate to the group elements actually, right?
Yes.
What do the Bx's translate to when V equals 1? So it's potentially.
I think it's still complicated. I have no good answer for that.
Okay. I think Humphreys have it, but I forgot. I've forgotten what the answer was. But Humphreys' book should have all of this, right? I mean, Humphreys developed the generic Hecke algebra, then the Kashtan-Lustig type of elements. But then, yeah, I forget. I never thought about what to do when you specialize Q equals 1 there.
Yeah, but I mean, there is an algorithm to calculate them. When I say it's complicated, there is an algorithm. In fact, exactly. you have a new algorithm developed like 1 month ago for some cases.
Yes.
But this algorithm, like you can calculate this Bx. It's just that it's the algorithm is complicated and you cannot get very far. That's the problem. So there are other algorithms that are better in different ways and stuff like that.
Right. Okay.
But I think that like if you specialize V equal 1, it will be the same. You will have like maybe there is a more satisfactory answer than that, but I don't know.
Right. In terms of the permutation group itself, what is the answer?
In the symmetric group, exactly. Okay. Yeah, maybe.
Or in the group algebra.
Mm-hmm.
Okay. Anyway, thanks.
Yeah, I was thinking of a general Coxeter group.
No, just for type A. Even for type A, what's the answer? Yeah. Okay. Thanks.
So I will do the same for circle bimodules, the same trick, the same dirty trick that I did here of just introducing Bx that are essentially like the thing that you want to calculate because you know Hx, you don't know Bx. Like you have to calculate it. For circle bimodules, it's the same. So you have R is the polynomials in n variables with complex, let's say with complex coefficients, and you have an action of the symmetric group here by permuting the variables. R is graded, so x1 has degree 1, say, and x1 to the power of 3 has degree 3. And there are some guys that are called the indecomposables. So the circle bimodules are graded RR bimodules. And there are some these people that are the bigs that, in fact, again, they are like the people that we want to understand. Like the category is defined in a very concrete way, again, like tensor products of stuff and direct sums of very concrete people. And there are these guys that we know that they exist, the indecomposables. And the objects here are just direct sums of shifts of these guys. So you take all the bigs, you shift them, and you make direct sums of this type of things, finitely many, and you obtain all circle bimodules. They are all sums of shifts of the bigs. So again, in circle bimodule land, the big quest is to really understand all these bx, like to how to construct them from scratch, and not in the sense of, like, we know that they exist and they are indecomposable and some other stuff, but we don't know exactly how to construct them. Well, and so I want to explain here what is the categorification that I was explaining. So remember that I said that the Hecke algebra was categorified by the circle bimodules. So what I mean is that when you add in the Hecke algebra, when you add, you will replace it by direct sum. When you multiply by V, you will replace it by shifting by 1. And when you multiply, you will replace it by tensor product. So here, when I write this means BS tensor product over R BS. So BS are bimodules, so you can tensor product over them. So this is the thing. So essentially, every formula you can invent in the Hecke algebra using the Kashtan-Lustig basis, the B, you will have the exact same formula in circle bimodules, and equality will be replaced by isomorphism. So, for example, BSRS times BSRS is equal to V cubed plus blah, 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 blah. Then you have that the tensor product of this indecomposable times the indecomposable corresponding to this. I forgot to say that BX goes to BX, of course. And so, for example, when you multiply by V cubed, this guy, then you shift by 3. You multiply by 2, it means that, and by BV to the power of 1, it means that you shift by 1 and it appears twice. And so that is the categorification theorem. That is like of course, there is a formalism where you say, like, you can go from the category to the Hecke algebra by applying a functor, the K0, the Grothendieck group, that but this is what really means. This is the meat of the categorification theorem. Essentially, that every formula in the Kashtan-Lustig basis will be replaced with a formula in the category, with an isomorphism in the category. And that's, like, incredibly beautiful, in my opinion. And then, sorry for the extremely fast forward, but a key step in the theory that was due originally, I would say, to, so Rouquier had the idea of presenting this category of circle bimodules by generators on relations, and Khovanov had the idea of making drawings, to draw maps, so this diagrammatic world. So they decided to draw maps. So you have a precise map between circle bimodules, and you draw it like this, for example. And so you define a new category that you call the diagrammatic Hecke category that has objects. The objects are sequences of points, of colored points. The color is there is one color for each element in in the so the symmetric group has simple reflections. The reflection 1, 2, 2, 3, 3, 4. This is the set S. S is the set of simple reflections. S1, S2, Sn minus 1. This will be the 1, 2, 2, 3. And in general, this is for every Coxeter system. But in this case, you have one color for each of these. And so objects will be sequences of colors, sequences of dots. And maps will be things like that. It will be some graph. Let me make it bigger. So this is a map from red, blue, red, green. Here you have red, blue, red, green, blue, red. This is a map from here to here. Here you have green, blue, red, green, blue, red. So this is the objects, and the maps are this kind of people. They are graphs which have only 6 valent vertices, like these ones, or things like this. These are the dots, or trivalent like this. And then you can put here inside, in floating, some polynomial. Here I should have written xs. These are like these are elements of R. So these are these people that you put. And so I am not explaining in detail this. I'm just saying that you define a category like this, and you define some relations between maps. So I don't know if you find a relation like this. If you have this map and you compose it with this, and you compose it with this will be equal to this, for example. You use some local relations, and you obtain the result that Sorgel bimodules is equivalent to this category over C. But why is this category so amazing? Well, it's beautiful. Calculations. Now you can prove stuff about algebra in totally topological ways, and that's how many things are proved now. But the truly marvelous thing about this is that this category, it's defined over FP, but the categorification theorem fails. But this, or in fact, I'm kind of lying. We don't know if the categorification theorem still works. But for this category, you just change here the coefficients that you put. You can put here coefficients floating, and you just change the coefficients to coefficients in FP. And then you have that this is still a categorification of the Heike algebra. So you will still have a map that it's the character map that categorifies the Heike category, and that takes the objects here and take it to an element in the Heike algebra. So this is like the good replacement of Sorgel bimodules to every characteristic. And then you still have here the indecomposable people. Here you have the indecomposables, and they go, the definition of the p-canonical basis in the Heike algebra is the image of the indecomposables in the Heike category, in the diagrammatic Heike category. And I have 1 minute. So here you have that these people, the p-canonical basis, are like the holy grail now to understand them, because they give us all the, for example, representations of the symmetric group in positive characteristic, or the representations of GLV in positive characteristic. They're essentially given by result of Jordi Williamson and Simon Rich and others by these things. So we are in the quest of understanding them. And just to finish, just to tell you that there are two like instances where this is like really understood. The first instance is when you are in A1 tilde. So if you don't know this affine value groups, classification and stuff like that, you just need to know that they are we are interested in the anti-spherical part. So this is given essentially by things like this, like is like the infinite dihedral group. And so you are interested in B of SR, and this you denote by Bn. And here I have a drawing of the 3 canonical bases in terms of the canonical basis. So you write it like when you write it like this, you draw, there are only ones that appear here. And you write it here as a drawing, and you will have a fractal. So why is this a fractal? Because you have this square, and you rotate it, and you obtain this one, and you translate it, and you obtain this one, and you repeat this process here, because we're in p = 3, and you obtain all of this square. And now what do? You take this one, you rotate it, and you obtain this one. You translate it, and you obtain this one. And you do it again, and you obtain this one. And what do you do now? You rotate it, you translate it. So it's a fractal. It's crazy. But what it's more crazy, and with this I really finish, is the conjecture for A2 tilde. So, oh, sorry, how can I stop this? So I don't know if you have seen this, but for A2 tilde, Lustig and Williamson and now Toga, Jensen have a, where is it? Here. A conjecture that I want to show just to finish my presentation. So this is a conjecture. And so let's explain you what is happening here. So in A2 tilde, you have that every dot represents an element of the group. And if you understand, so what we are seeing are the p-canonical basis of the elements here, the dots here in the wall, what it's called the wall. And if you understand this by representation theory things, you understand everything else. You understand people inside. So that's why this wall is so important. So what they are showing is like, now they are showing the p-canonical basis of this in terms of the canonical basis. So they are saying that it appears this guy plus this guy, and the color means the number, how big the number is. So that's why this is a billiards, because it seems like billiards bouncing on the alcoves. And so also here, I think there is a hidden fractal structure in some sense, but there is lots of stuff we don't know. Imagine that A2 tilde, and the conjecture is not for the whole work, the whole wall. It's only for like you can go until p square or something like that. It's like you know a little bit part of the wall, and so just to finish. What is it? Oh, I lost it. To finish the I have almost no battery. Sorry, I forgot what I wanted to say.
You told us about the A2 tilde billiards conjecture, and then after that, it's only until p square, and then.
Yeah. I just wanted to say that so the p square is like something that like they have this Lustig invented this generational philosophy that means that you like it's complicated, but essentially you have a different behavior in less than p square, less than p cube. They understand the second generation. And Jordi has a way of understanding this, like a very conjectural, and he's trying to do this, a way of understanding this, that it's related with categories related to the stable homotopy of spheres. So the homotopy of spheres is like a crazy problem, and we always thought with Jordi that this was so crazy that maybe it was related to the homotopy of spheres because it was so crazy. And then now it's real. Like there are some ways to understand it that is related to the homotopy of spheres. And going back to what I said in the beginning, Yuri Manin has a way to understand also this geometry over F1, that it's very related to the stable homotopy of spheres. So that's all. Thank you very much.
Okay, well, Thank you, Nicolas, for a very, very engaging and extremely, by the end, extremely mysterious talk. And yeah, let us hope that sooner rather than later, maybe even in our lifetimes, some of these connections are really laid down, and yeah, maybe we get from affine SL3 or affine A2 to stable homotopies of spheres and billiards to F1 to maybe the Riemann hypothesis. That's what Manin wants to say. Manin and Konzen, as you said. So anyway, thank you for a very nice talk. And are there any further questions? Other questions for him? There were already several during the talk, but yeah. Okay, well, if not, then let's again thank the speaker again, especially for giving the talk in the middle of almost fully well COVID. But yeah, I'm glad that you are well enough to give the talk, and I hope you continue to be fully well.
Yeah, thank you very much. And I'm so sorry that I couldn't give it last time.
No.
Because of the COVID.
No, absolutely. Very glad to have you give the talk. Yeah, I'll be in touch, of course, by email as well. Yeah. It's nice to see you after many years.